Welcome to module 3 of chapter 4. In this chapter we are going to prove two important lemmas which are useful to prove quadratic reciprocity laws. One of them is Gauss Lemma, which is going to evaluate Legendre symbol A by P, where P is an odd prime. Of course, Euler's criteria also establishes to know whether given A is a quadratic residue or not, but this Gauss Lemma allows us to give the value very conveniently, and we are also going to evaluate the Legendre symbol 2 by P for various primes P. In chapter 4 in module 3 we are going to discuss about Gauss lemma and followed by another lemma, but its name is written as Gauss lemma. So, the learning objectives of this module are Gauss criterion for quadratic residues, finding all primes P such that 2 is a quadratic residue modulo P or not. So, first we are going to state what is a Gauss lemma. Let P be an odd prime and let GCD of A comma P equal to 1 if n denotes the number of integers in the set S equal to A, 2A, 3A and so on P minus 1 by 2 into A, whose remainders upon division by P exceeds P minus P by 2, then A by P, that is Legendre symbol A by P, is equal to minus 1 whole power n. So, we will repeat. This says that let P be an odd prime and GCD of A comma P equal to 1 if n denotes the number of integers in the set S, A, 2A and so on P minus 1 by 2 into A, and afterwards we will take all these numbers are division, we will divide it by P and we will take the remainders. If the n represents the number of numbers in S which are greater than P by 2 in those remainders, then this A by P is exactly equal to minus 1 whole power n. So, it is a nice criterion to know whether given A is a quadratic residue modulo prime or not. So, the proof goes like this. Let U1, U2 and so on Un be the remainders satisfying P by 2 is less than Ui is less than P. These are the numbers which we got by dividing elements in S by P. These are the remainders. And V1, V2 and so on Vm be the remainder satisfying 1 is less than or equal to Vj is less than P by 2. Then it is easy to see that m plus n is equal to P minus 1 by 2. Note that the integers V1, V2 and so on Vm, comma P minus U1, P minus U2 and so on P minus Un are all positive, distinct and less than or equal to P minus 1 by 2. It is because U1, U2 and so on Un, they are all greater than P by 2. So, P minus U1, P minus U2 and so on P minus Un are going to be less than P minus 1 by 2. Since P is an odd prime, P by 2 is not an integer. So, they are less than P minus 1 by 2. Consequently, V1, V2 and so on Vm comma P minus U1, P minus U2 and so on P minus Un are all rearrangement of the numbers 1, 2, 3 and so on P minus 1 by 2. But for this one has to establish that V1, V2 and so on Vm comma P minus U1, P minus U2 and so on P minus Un are all distinct. So, that is easy to show. So, just assume that the two of them are equal, then you can prove that we are going to get a contradiction. So, hence we are proceeding. So, hence V1 into V2 into and so on P minus U1, P minus U2 and so on P minus Un is nothing but 1 into 2 into 3 up to P minus 1 by 2 modulo P, or equivalently this is equal to minus 1 whole power n into V1, V2 and so on Vm, U1, U2 and so on Un. It is because P minus U2 is nothing but minus U2 modulo P, P minus U1 is nothing but minus U1 modulo P and so on P minus Un is nothing but minus Un modulo P. So, we are going to get minus 1 whole power n into this quantity, but 1 into 2 into 3 up to P minus 1 by 2 is nothing but P minus 1 by 2 factorial. So, we have this equation 1. Now, by definition V1 into V2 and so on Vm into U1, U2 and so on Um is nothing but A, 2A, 3A and so on, p minus 1 by 2 into A. These are actually elements taken from S. So, this is equal to product of like that. So, which is equal to A power p minus 1 by 2 into p minus 1 by 2 factorial modulo p. So, hence now this is an equation 2. So, from equation 1 and 2 if you compare, we are going to get A power p minus 1 by 2 is congruent to minus 1 whole power n modulo p. But we know that A power p minus 1 is congruent to A by p less than the symbol A by p. So, hence we have the required part. Now, we are going to illustrate this Gauss lemma with an example. So, illustration of Gauss lemma with an example. Let us take A equal to 7 and P is equal to 17. That is then 7 into 1 modulo 17, 7 into 2 modulo 17 and so on, 7 into 6 modulo 17 up to we are taking 7 into 8 modulo 17. It is because P is equal to 17. So, we have to go up to P minus 1 by 2, that is 8. So, if you consider these numbers, these are equal to 7, 14, 4, 11, 1, 8, 15, 5. So, since 17 by 2 is 8.5, so we are went up to 8 only. Hence, these the 3 numbers 14, 11, 15 only greater than p by 2. So, in the Gauss lemma we are counting, we are looking for n. N is the number of residues or remainders which are greater than p by 2. So, in this case there are only 3 are there. So, 7 by 17 is equal to less than the symbol equal to minus 1 whole power 3. So, which is equal to minus 1. That means that 7 is not a quadratic residue mod in 17. So, Gauss lemma. By using Gauss lemma, it is much easier to prove whether given number A is a quadratic residue or not. So, where if you choose A equal to 17 and P equal to 7, then we need to compute only 3 values, 17 into 1 mod 7, 17 into 2 mod 7 and 17 into 3 mod 7. So, 362. So, again in this case the numbers which are greater than 7 minus 1 by 2 is only 1, that is 6. So, again we have 17 by 7 is also equal to minus 1. So, 7 is also 17 is not a quadratic residue modulo 7. So, now we are going to compute the values of 2 by p. Here 2 by p means we are going to evaluating the Legendre symbol 2 by p. That means we want to find out what are the primes for which this 2 is a quadratic residue modulo p. So, the theorem statement is that if p is an odd prime, then 2 by p is equal to 1 if p is congruent to 1 mod 8 or p is congruent to 7 mod 8, and which is equal to minus 1 if p is congruent to 3 mod 8 or p is congruent to 5 mod 8. So, we covered all the primes now. So, now we computed Legendre symbol 2 by p for all primes p. So, we are going to prove this result now. Since p is an odd prime, GCD of 2 comma p is 1, thus we can apply Gauss lemma. So, that is A is equal to 2, though we have to consider the set S is equal to 2 into A into 1, A into 2 and so on, p minus 1 by 2 into A. So, that is 2 into 1, 4 into 1 and so on, p minus 1 by 2 into 2. So, we are going to get S equal to 2, 4 up to p minus 1. So, that let us compute n for different values of the prime p. So, the case 1 is when p is of the form 4k plus 1, then the numbers 2k plus 2 is equal to p plus 3 by 2, p plus 7 by 2 and so on, p minus 1 are elements of S that exceed p by 2. That is that in this case n is equal to p minus 1 by 4. Hence, 2 by p, Legendre symbol 2 by p is equal to minus 1 whole power p minus 1 by 4, which is equal to minus 1 whole power k. Therefore, we will see that 2 by p is 1 whenever k is even, that is that corresponds to p is congruent to 1 mod 8 and p 2 by p is equal to minus 1 whenever k is odd, or that is corresponds to p is congruent to 5 mod 8. Now, we will see another case, that is p is equal to 4k plus 3. In this case, the numbers 2k plus 2 is equal to p plus 1 by 2, p plus 5 by 2 and so on, p minus 1 are elements of S that exceed p by 2. Thus, in this case n equal to p plus 1 by 4. Hence, 2 by p is equal to minus 1 whole power p plus 1 by 4 is equal to minus 1 whole power k plus 1, since we are assuming p is equal to 4k plus 3. Therefore, as above, 2 by p equal to 1 whenever k is odd, that corresponds to p is congruent to 7 mod 8, and 2 by p is equal to minus 1 whenever k is even, that corresponds to p is congruent to 3 mod 8. So, we state a corollary of the above theorem, which follows from the fact that p square minus 1 by 2 is even if and only if p is congruent to 1 mod 8 or p is congruent to 7 mod 8. Hence, we omit the proof. So, the corollary says that if p is an odd prime, then 2 by p is equal to minus 1 whole power p square minus 1 by 2. So, this is a nice interpretation for 2 by p. So, the one of the problem is, if p is a, let p be a prime of the form p congruent to 7 mod 8, then prove that p divides 2 power p minus 1 by 2 minus 1. The solution goes like this. So, by previous theorem we know that 2 by p is equal to 1 whenever p is of the form p is congruent to 7 mod 8. Therefore, 1 is equal to 2 by p, which is congruent to 2 power p minus 1 by 2 modulo p. So, obviously, p divides 2 power p minus 1 by 2 minus 1. So, as we know that A is congruent to B mod n implies n divides A minus B. So, from that we will get this part. So, now we will look at another example. It says that if n belongs to 11, 23, 83, 131, 179, 183, 239 or 251, then 2 power n minus 1 is a composite number. So, here it looks like there is no need of quadratic residues, but by using quadratic residues problems of this type can be solved very easily. The solution goes like this: if let n belongs to one of these, then 2n plus 1 belongs to 23 or 47 or 167 and so on 503. The set contains primes exactly of the form 8k plus 7, and therefore, from the above problem we see that 2n plus 1 divides 2 power n minus 1 as n is equal to p minus 1 by 2. Thus, we got the required result. Now, we are going to prove one of the another important lemma called Eisenstein's lemma, which is going to evaluate the Legendre symbol A by p, where A is any odd integer and p is an odd prime, which is in fact very useful in proving quadratic reciprocity law. This we are going to prove in the next module. Now, we are going to state and prove Eisenstein's lemma. Eisenstein's lemma says that let p be an odd prime and let A be any odd integer with GCD of A comma p equal to 1, then A by p is equal to minus 1 whole power t of A comma p, where t of A comma p is defined as summation j is equal to 1 to p minus 1 by 2 j A by p, where box of x denotes the largest integer less than or equal to x, or also called box function or greatest integer function. So, recall that the numbers v1, v2 and so on vm comma p minus v1, p minus u1, p minus u2 and so on p minus un, in the proof of Gauss lemma we showed that they are all positive, distinct and less than or equal to p minus 1 by 2. Moreover, we saw that ui's and vj's are obtained as a remainders when ka for 1 less than or equal to k less than or equal to p minus 1 is divided by p. So, also by division algorithm, for each k 1 less than or equal to k less than or equal to p minus 1 by 2, we obtain the integers qk and tk such that ka is equal to qk into p plus tk, with 1 less than or equal to tk is less than or equal to p minus 1. Consequently, qk is equal to, again recall qk is obtained from in the equation ka equal to qk into p plus tk, that is qk is the quotient if you divide ka by p. So, consequently qk is equal to qk plus tk by p, okay, which is equal to ka by p. Thus, we have that ka is equal to qk value we can substitute now, that is ka by p into p plus tk, with 1 less than or equal to tk less than or equal to p minus 1. We further see that summation k is equal to 1 to p minus 1 by 2 ka, which total sum is equal to summation k is equal to 1 to p minus 1 by 2 ka by p into p plus tk, but tk are set of all remainders when we divide all the numbers by p. So, these are nothing but u1, u2 and so on un and v1, v2 and so on vn. So, summation tk is nothing but summation I is equal to 1 to n ua plus summation j is equal to 1 to m vj. So, from again from theorem 1 Gauss lemma we recall that the numbers v1, v2 and so on vm comma p minus u1, p minus u2 and so on p minus un were a rearrangement of the numbers 1, 2, 3 and so on p minus 1 by 2. Hence, summation k is equal to 1 to p minus 1 by 2 k, which is equal to I is equal to 1 to n p minus ui plus summation j is equal to 1 to m vj, which is equal to pn plus summation j is equal to 1 to m vj minus summation j is equal to 1 to n ui. So, by substituting equation 4 in equation 3, we are going to get a minus 1 times summation k is equal to 1 to p minus 1 by 2 k is equal to p times summation k is equal to 1 to p minus 1 by 2 ka by p box function minus n plus 2 times summation I is equal to 1 to n ui. But we know that p is congruent to a is congruent to 1 mod 2, since p is an odd prime, a is also odd. In the hypothesis in the Eisenstein's lemma, this is important. It cannot evaluate a by b for all a, it evaluates only, it is giving answer only when a is an odd number. So, a is congruent to 1 mod 2. So, in the equation now it becomes a minus 1 is congruent to 2 modulo 2. So, we are going to get that summation k is equal to 1 to p minus 1 by 2 ka by p minus n is congruent to 0 mod 2. So, that is equivalent to n is congruent to k is equal to 1 to p minus 1 by 2 ka by p modulo 2. In other words, n and k is equal to 1 to p minus 1 by 2 ka by p have same parity, that means both are even or both are odd. But we know from Gauss lemma that a by p is equal to minus 1 whole power n. So, but n value now we can replace it by summation k is equal to 1 to p minus 1 by 2 ka by p. So, we proved the Eisenstein's lemma. Now, we will illustrate the Eisenstein's lemma with an example. So, we are trying to evaluate 7 by 11. The solution goes like this: 7 by 11 is equal to minus 1 whole power summation k equal to 1 to 11 minus 1 by 2 into k into 7 by 11, that is k value takes from k equal to 1, k equal to 2, k equal to 3, 4 and 5. So, minus 1 whole power greatest integer function 7 by 11 plus greatest integer function 2 into 7 by 11 and so on plus 5 into 7 by 11. So, which is equal to minus 1 whole power 0 plus 1 plus 1 plus 2 plus 3, which is equal to minus 1. That means that 7 is not a quadratic residue modulo 11. Similarly, we can compute 11 by 7 as well. So, 11 by 7 is equal to minus 1 whole power k equal to 1 to 7 minus 1 by 2 summation k into 11 by 7, which is equal to minus 1 whole power 11 by 7 plus 2 into 11 by 7 plus 3 into 11 by 7, which is equal to minus 1 whole power 1 plus 3 plus 4, which is equal to 1. It is easy to see that 7 and 11 both are congruent to 3 mod 4. So, that is why if one is a quadratic residue, other is not a quadratic residue. These things we will establish in near future, but here we saw just try to remember this value, that one of the value is minus 1 and other is plus 1. So, now let p be an odd prime and let a comma k belongs to natural numbers such that a comma p, GCD of a comma p and GCD of k comma p equal to 1, then a by p equal to 1, that is Legendre symbol a by p equal to 1, or a is a quadratic residue modulo p whenever the equation x square minus ay square equal to kp admits a solution. So, it is one of the important property that, so it is establishing that a is a quadratic residue modulo p if and whenever the equation x square minus ay square is equal to kp admits a solution. So, the proof goes like this. Here observe that there are two variables involved. So, that is why let us assume r comma s be a solution of x square minus ay square equal to kp, then we have that r square minus as square is equal to kp. So, that is equivalent to r square is congruent to as square modulo p. Hence, r square into s power 2p minus 4, which is equal to congruent to a into s square into s power 2p minus 4. That means, just we multiplied both sides by s power 2p minus 4. So, which is equal to a times s power p minus 1 whole square modulo p. Since s comma p is 1, so by Fermat's little theorem, s power p minus 1 by 2 is congruent to 1 mod p. So, we are going to get this part, that is, since GCD of k comma p equal to GCD of a comma p equal to 1, we have GCD of s comma p equal to 1. So, for Fermat little theorem, s power p minus 1 is congruent to 1 mod p. So, therefore, rs power r into s power p minus 2 whole square, which is equal to r square into s power p 2p minus 4, which is congruent to a times s power p minus 1 whole square, which is congruent to a mod p. That means that a is a satisfying the equation x square is congruent to a mod p. That means, a is a quadratic residue modulo p. Thus, we have a by p equal to 1. But converse of this result is not true. That is easy to verify, but that is we can find a prime p and integers a and k such that GCD of a comma p and GCD of k comma p equal to 1 and a Legendre symbol a by p equal to 1, but the equation x square minus ay square equal to kp has no solution. For example, let us take p equal to 7 and a equal to 4 and k equal to 1, then it is easily verified that GCD of a comma p is equal to GCD of k comma p is equal to 1. Also, a by p is equal to 1, as 4 is a quadratic residue modulo 7. So, 4 by 7 is equal to 1, but it can be easily checked that using the modulo 4 congruence, that x square minus 4 y square is equal to 7 does not have any integer solution, as x square is congruent to 0 or 1 mod 4. Let p is congruent to plus or minus 3 mod 8, then the equation x square minus 2y square is equal to p has no solution. So, this is another problem. Here we say that if p is congruent to plus or minus 3 mod 8, then the equation x square minus 2y square equal to p does not have a solution. That means we are solving some Diophantine equations by using quadratic residues. The proof goes like this: if x square minus 2y square equal to p has a solution, then we saw by in the proof of previous result that x square is congruent to 2y square mod p, hence 2 is quadratic residue modulo p. So, a contradiction to earlier result. So, it has been shown that 2 by p is equal to minus 1. It is because whenever p is congruent to plus or minus 3 mod p mod 8, then 2 by p is minus 1. 2 is not a quadratic residue. So, which is contradiction to that problem. Now, we are going to show that if both p and 2p plus 1 are odd primes, then we are going to show that minus 1 whole power p minus 1 by 2 into 2 is a primitive root modulo 2p plus 1. That is, the statement is like this: let p and 2p plus 1 both are odd primes, then minus 1 whole power p minus 1 by 2 into 2 is a primitive root modulo 2p plus 1. So, proof: let q is equal to 2p plus 1, since p is an odd prime, so obviously q is greater than or equal to 7, and order of 2 and order of minus 2 belongs to 1 or 2 or p or 2p only, as phi of q is equal to 2p. So, order of 2 or order of minus 2 has to divide 2p. That is why these are belongs to 1 or 2 or p or 2p. Further, it is easy to see that order of 2 modulo q or order of minus 2 modulo q does not belongs to 1 comma 2. That means orders are not going to be 1 or 2. If that is, if order of 2 is equal to 2 or order of minus 2 modulo q is 2, then we are going to get q divides 3, which is a contradiction that q is greater than or equal to 7. Hence, order of 2 and order of minus 2 modulo q is belongs to p or 2p, or its values either p or 2p. Now, it is sufficient to show that this order of q minus 1 whole power p minus 1 by 2 is not equal to p, then it is going to be 2p and we are done. So, we show this by using two cases. Assume that p is congruent to 1 mod 4. In this case, q is congruent to 3 mod 8, that is minus 1 whole power p minus 1 by 2 is equal to 2, and 2 by q is equal to minus 1, or equivalently 2 power p is minus 1. Hence, since 2 power p is minus 1, so 2 power 2p is going to be 1. So, order of 2 is equal to 2p, which is phi of q. Now, we look other case that p is congruent to 3 mod 4. In this case, q is congruent to 7 mod 8. So, minus 1 whole power p minus 1 by 2 into 2 is equal to minus 2, and 2 by p equal to 1, as q is congruent to 7 mod 8. So, 2 is a quadratic residue modulo q. Hence, minus 2 by q is equal to minus 1 by q into 2 by q, which is same as minus 1 by q, which is equal to minus 1. So, hence order of minus 2 is also 2p, or phi of q. Now, we are going to show another important property, that there are infinite number of primes of the form 8k minus 1. The statement is there are infinite number of primes of the form 8k minus 1. The proof goes like this: let p1, p2 and so on pk be infinite number of primes of the form 8k minus 1. Consider the value p is equal to 4 times p1 into p2 and so on pk whole square minus 2. Then it is easy to see that p is of the form 8k 16k minus 2. Let p be any prime divisor of capital P, then 4 into p1, p2 and so on pk whole square is congruent to 2 mod p, or equivalently 2 is a quadratic residue modulo p, or 2 by p Legendre symbol is 1. Hence, p is of the form 8a plus 1 or 8a minus 1. If every odd divisor of p is of the form 8a plus 1, then p is of the form 16k plus 2, as 2 divides p, and also as 2 divides p. Hence, there exists a prime divisor q of p of the form 8a plus 1, which is different from p1, p2 and so on pk. That means, we able to we are able to give, we produce a new prime which is different from P1, P2 to Pk, and which is of the form 8k minus 1. So, hence we got the required proof. In this module, we proved important results lemmas. One is Gauss lemma, other is Eisenstein's lemma. We also showed that whenever p and 2p plus 1 both are odd primes, then we established that minus 1 whole power p minus 1 by 2 into 2 is a primitive root modulo 2p plus 1. We also showed that there are infinitely many primes of the form 8k minus 1. With this, we end this module.